Thin cylinders is very simple, fundamental formula. They are not asking any question from thin cylinders. Only wire wound problem will be taken to the examination consideration. But examination point of view, thick cylinders are very important. Exam point of view, or so here cylinders are commonly used as a component of machineries and chemical plants, and usually they are subjected to internal and external tests. That's cylinders is a thin elements, like RCS slabs is a thin element, and plates is a thin element. Similarly, the cylinders are the thin element subjected to internal and external pressure. That is called. Um, so here, how can you differentiate thin and thick? Depending on thickness of the shell or thickness of the cylinder, you can differentiate thick and thin cylinders. So when the thickness of the cylinder is less than 1/10 to 1/15 of its radius. So cylinder, already all of you know cylinder. What is cylinder? It is a circular cone cylinder having diameter and length. So the thickness of the cylinder is less than 1/10 to 1/15 of cylinder. Then that is called as a thin cylinder. So this is a thin cylinder. The stress in radial direction is negligible in thin cylinders. When the thickness of the radius is more than that 1/10 to 1/50th radius, that is called a thick cylinder. Obviously, it is called as a thick cylinders. So coming to the thin cylinders, the in thin cylinders, uh, in the analysis of thin cylinders, we are assuming 2 points. One is radial stress is very small and it is negligible in the thin cylinders. So what is radial stress? What is long-term stress will be shown in the figures. The stress in radial direction is negligible in thin cylinders. Actually, it is there. The stress in the in radial direction is there, but we are in the analysis we are neglect that stress in radial direction, and also stress is considered uniform. Using these two uh, assumptions, we can analyze the thin cylinders. So, in the analysis of thin cylinders, the following assumptions are made. One is radial stress is small or negligible or neglected. Hoop, and that means hoop stress and long-term stress. Here, in thin cylinders or thick cylinders, whatever it may be, in cylinders, there are two important stresses will be coming to the picture. One is a circumferential stress that is called another, or it is called as a hoop stress. This is acting diametrical section, and another one is long stress. These two stresses are very important. So in the analysis of thin or thick, there are main two stresses are hoop stress and long stress, or circumferential stress or long stress. So the hoop and long stress distribution is uniform in the case of thin cylinders. In the case of thick cylinders, it is not uniform. That is enough. So, in the analysis of thin cylinders, one is assume radial pressure is neglected, and second one is stresses in the cylinders is act distribution across the section is uniform. So, let us consider thin cylinder, which is diameter is D and thickness T and length L, and ends are closed. Obviously, cylinders are one end is closed, another end is open. After filling the liquid or any chemical, then that will another end is also opposite end is also closed. So you are assume the cylinder is having diameter D and thickness T and length L, ends are closed. The even the internal pressure P will be, that means internal fluid pressure P.
Your voice the
Then
question.
okay na, right? Now voice is clear. Okay, na?
No, sir. Voice is breaking, sir.
Voice is breaking.
వాయిస్ తక్కువ.
వాయిస్ తక్కువగా వస్తుందా? ఓకే, నౌ 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 ఓకే, వాయిస్ ఇస్ ఓకే, క్లియర్. ఇప్పుడు క్లియర్గా వస్తుందమ్మా వాయిస్? రైట్ రైట్ రైట్. సో రైట్ సార్, రైట్. So when the fluid pressure will be applied into the or admit into the cylinder, obviously two types of stresses will develop, which is circumferential direction is F1. That is called F1 is called hoop stress. This stress is acting in diametral section. That's why it's called a circumferential stress or hoop stress, which is denoted by F1. That is called PD by 2T. That's a simple derivations. You remember only F1 is equal to PD by 2T. That's enough. Okay. And second, acting along the length of the cylinder, it is called longitudinal. That means longitudinal stress will be acting in the longitudinal direction, which is denoted by F2. That is PD by 80. So this is the figure. All of you note down all these things. This is the cylinder. This is the longitudinal axis, and this is the longitudinal axis, and this y is the circumferential line. So take any element. Already I told the diameter of the cylinder d and length of the cylinder is L, and the thickness of the cylinder is T. This is thickness of the cylinder is T. So take any element on the cylinder subjected to two stresses. That is called, one is circumferential stress or hoop stress is F1 in acting and diametrical section. That's why it is called circumferential stress, which is denoted by F1. Need not to worry about the derivation, but you remember this formula PD by 2T. That's enough. If here P is the internal fluid, D is the diameter, T is thickness. If you know the D and T and fluid, you can calculate the hoop stress on the cylinder. And F2 is acting longitudinal direction, which is called as the denoted F2 PD by 40. And if internal fluid pressure will be internal fluid pressure, that means maximum, that means if the internal pressure or radial pressure is very small, then the F1 and F2 will be major. Therefore, major principal stresses. Then use principal stress concept. You can find the shear also. What is the you are studied in mechanics of methods of mechanics or mechanics of solids? What is the, if you have sigma 1 and sigma 2 are the principal stress, major principal and minor principal? What is the maximum shear stress? Hello.
Central axis.
Yeah, maximum shear stress is equal to average of difference of the both stresses. That means sigma 1 minus sigma 2 by 2 is the tau maximum shear stress. So like that, that means here F1 shear maximum shear stress on the cylinder will be F1 minus F2 by 2. So F1 is equal to PD by 2 to F2 is equal to PD by 40 by 2 means nothing but PD by 80. So maximum shear stress is equal to PD by 80. Like that, a bit questions will be coming on this thin cylinders. So thin cylinders is majorly asking bits. Okay. So F1 is the PD by 2 to hoop stress. One is the one major principal stress. Another one is minor principal stress is F2. That is longitudinal stress PD by 40. Then maximum shear stress tau maximum. That means in thin shells, only in thin cylindrical shells. So half of sigma 1 by 2 into sigma F1 by F1 minus F2, which is give PD by 80. Okay. So that is the here I not write then just use principal stresses, that's enough. And change in dimensions of the cylinders. Now you calculate the change in dimensions d by d when internal fluid pressure is subjected to thin cylinders, not thick. So delta d by d is equal to, this is the formula. Use F1 by E, or otherwise F1 by E. I will not show here. Already you studied in simple stress and strain in mechanics of solids. That's why I not mentioned here. F1 by E minus mu times F2 by E. Then you get this equation. PD by 4TE by 2 minus mu. And similarly, this is also formula. PD by 4TE is common for all change in diameter, length, and volume of the cylinder. So only variable terms is bracket, what the parameters within the bracket, 2 minus mu, 1 minus 2 mu, change in length, and 5 minus 4 mu is the change in volume. So just you remember all these values, and if anybody, if you know the P, T, E values and mu values, one question is asking what is the hoop stress, what is the longitudinal stress, what is the change in diameter, or what is the diameter, and what is the change in length, what is the change in volume. So you directly use these equations and determine the other parameters. So this is the thin cylinders, analysis of thin cylinders. And exam point of view, in thin cylinders, they ask one question: wire wound cylinders. This is the important in the examinations from the thin cylinders. That's enough. So I will tell later, or explain this wire wound problem, wire wound cylinders. I will complete this one. So all of you put the heading wire wound cylinder. This is the maybe examination question from the thin cylinders, not thick, thin cylinder. Thin cylinders అడిగితే ఇది అడగచ్చు, the wire wound cylinders అడగచ్చు. So wire wound cylinders is nothing but carry to improve the resist the maximum or heavy fluid pressures by wound the extra wire on the pipe. Then it's called wire wound problem. So in the cylinders, the strengthened cylinders will be strengthened by closely winding the wires under tension, which is in the case of stresses, all stresses are in tensile nature, not in compressive. In the previous one, whether it is a hoop stress or is a longitudinal stress, the nature is only tensile. There is no compression. There is no compressive nature. Compressive nature. That is one of the why, because when you see the figure, I will draw the forces only tensile nature. See, F1 is tensile nature on both sides, and F2 is also tensile. So whatever it may be, in thin cylinders, the nature of the stresses are in tensile. That you remember that one majorly. So uh, let us all of tension that, yeah, already all of you know wires are is in tensile nature. So those wires will be wound on the pipe. So the tension in the wire gives the external pressure on the cylinder. Hence, introduce the compressive hoop stress in the cylinder. That is the important. Here in wire wound problem, the compressive nature, that is also a thin wire, tensile wire, a steel wire, which is in tensile nature. But that tensile stress in the wire will be act as a compressive force on the cylinder when you wound the wire to the cylinder. So that is I will mention the tension in the wire. Listen carefully. The tension in the wires gives rise to external pressure on the cylinder, and hence introduce the compressive hoop stress in the cylinder. So when internal pressure is applied, the hoop tension is induced. Hence, the net hoop tension is the algebraic sum of the about two type of stresses, which is obviously less than the hoop tension, which is given a PD by 2T. This is the wire wound technique. This technique is used to strengthen the thin cylinders by carrying heavy pressure liquids. Listen to it, students. అర్థం why
Sir.
you are used wire wound cylinders and thin cylinders means this this is the main concept. So to this how it is interacting. సో మీరు ఒక పల్చటి అంటే థిన్ వైర్, వైర్స్ అంటేనే ఇట్ ఈస్ ఓన్లీ టెన్సైల్ నేచర్. సో ఆ వైర్ని మీరు ఒక సిలిండర్కి చుట్టారు అనుకోండి రౌండ్గా, అప్పుడు టెన్సైల్ స్ట్రెస్ ఇన్ ద వైర్ విల్ బి యాక్ట్ ఆన్ ద ఎక్స్టర్నల్ ప్రెషర్ ఆన్ ద cylinder as a compressive hoop stress. So in that situation, you applied or you admit the fluid pressure into the cylinder, then what will happen? That hoop stress will be the algebraic sum of internal initial and admitted fluid pressure will give the net hoop stress. So therefore, whenever the hoop stress will be reduced than the initial, it capacity will be increased to carry the high pressure fluids. That is the technique used in the wire wound problem. Okay, let us take a D dash is the diameter of the Y and D is the diameter of the cylinder. D dash is the diameter of the Y and D is the diameter of the cylinder and T is the thickness of the cylinder and L be the length of the cylinder and F W naught. The naught is mentioned for the initial tensile stresses in steel wire. W is meant for Y. F is stress. So stress in steel wire in tensile nature. Similarly, initial compressive stress in cylinder when you this steel wire is wound upon the cylinder is subjected to compressive hoop stress. That is called FC, initial compressive stress in cylinder. Let us see the figure. This is the L, and ఈ గీతలో ఉన్నది చూడండి. This is the cylinder, which is the diameter of the cylinder is D, and the length of the cylinder is L, and you wound a thin or thin wire, steel wire. This is the wire with diameter is D dash. So this is the longitudinal section, and you take the cross section. So diameter of the cylinder, and this is the thickness of the cylinder, and the outer ring will be the diameter of the wire. Have you seen this figure? All of you draw this figure. అడిగితే వైర్ బౌండ్ ప్రాబ్లం అడుగుతాడు థిన్ సిలిండర్స్ నుండి, అందుకంటే ఇంకేం లేదు. మిగతా అన్ని కూడా డైరెక్ట్ ఫార్ములా సబ్స్టిట్యూషన్. ఆల్రెడీ నేను ఐ విల్ ఆర్ యూ కాపీడ్ దిస్ ఆల్ దిస్ థింగ్స్? టైం ఏమన్నా స్టూడెంట్స్ మీరు కాపీ చేసుకుంటారా ఇవన్నీ కూడా? టైం కావాలా కాపీకి? అమ్మా
Yes, sir.
కాపీ చేసుకో. థిన్ సిలిండర్స్ కాపీ చేయడం టైం కావాలంటే కాపీ చేయండి. టైం ఇవి థిన్ సిలిండర్స్ అనే డైరెక్ట్ ఫార్ములాస్ కాబట్టి పిడిఈ తెలిస్తే పిడిటిఈ ఇచ్చేస్తాడు వాడు. ఇచ్చేసిన మ్యూ కూడా ఇచ్చేస్తాడు. ఇచ్చి ఫైన్ కనుక్కో ఫైండ్ ఆల్ దీస్ థింగ్స్ అంటాడు. అవి ఎవరైనా చేస్తారు సబ్స్టిట్యూషన్ అండ్ గెట్ ద ఆన్సర్. కానీ ఇది అడగడు. బట్ ఈ వైర్ బౌండ్ ప్రాబ్లం అడుగుతాడు బాక్స్ in thin from the thin cylinders. కాపీ చేసుకోండి. నేను చెప్పుకుంటా పోతే అలా 12 2 గంటలు 3 గంటలు చెప్తాను. యూ షుడ్ కాపీ ఆల్ దీస్ థింగ్స్. Hello.
ఎలా అదే
Hemant.
Language.
మిమ్మల్ని అందరినీ బార్డర్లో పెట్టాలబ్బా, బార్డర్లో పెట్టి పని చేయించారు. ఇప్పుడు దేశభక్తి పెరుగుతుంది. కాపీ చేస్తే అయిపోయింది చెప్పండి, నేను స్లైడ్ మారుస్తాను. Are you copied? All these formulas?
Yes, sir.
Okay. Now put a heading. All this from this figure and also.
Sir,
Screen sharing.
Screen share అయిపోయింది.
అయిపోయిందా? ఓకే.
స్క్రీన్ షేర్ ఆగిపోయింది సార్, రావట్లేదు.
ఆహా, స్క్రీన్ షేర్ అయిపోయిందా? ఎట్లా అయింది ఇది?
సార్
ఓకే సార్.
ఓకే
సార్
ఆ,
ఈ చేంజ్ ఇన్ డయామీటర్ కి PD స్క్వేర్ బై 2T అని ఇచ్చారు సార్. లాస్ట్ స్లైడ్ సార్,
ఎక్కడ?
ప్రీవియస్ స్లైడ్ సార్. చేంజ్ ఇన్ డయామీటర్ కి PD స్క్వేర్ అని ఇచ్చారు సార్ ఇక్కడ మెటీరియల్ లో.
తప్పు ఇది స్క్వేర్ అండి, డి స్క్వేర్ రాదు. చేంజ్ ఇన్ డయామీటరా? డయామీటర్ డెల్టా డి బై డి
సార్.
అంతే కదా, డెల్టా డి బై డి. వై?
ఓకే సార్, ఓకే సార్.
డి స్క్వేర్ రాదమ్మా, అది ఎక్కడ కూడా స్క్వేర్ అనే పదం రాదు అన్నిట్లో కూడా.
ఓకే, అంటే కింద డి నటు తీసుకెళ్ళారు.
లేదు. Right. One problem. You can take the first half of the diameter to find the initial stress consider the equilibrium of half of the cylinder. So in that I've already here Fw not equal to initial tensile stress, and this is the initial tensile nature, uh, initial tensile nature of the wire, and F not EC, it's a compressor hoop concentrator. So force exerted by 1 ton of wire is given by area into full term కాబట్టి into 2 in 2 times into pi by 4 d dash whole square, it's the area multiply the stress in that wire, gives the force. So number of turns in a length will be determined L by d dash. Now this will give the number of turns. So total force exerted by the wire is equal to this force exerted by 1 ton into number of tons. So this is the equation A. So this resisted by compressive force developed, which is resisting force, will be Fc into that area T into L, and మొత్తం టోటల్గా ఉంటుంది కదా 2 times in 2 times. So this is the resisting force taken as a B equation. So equating the equation A and B, you get the Fc. That means hoop comes cylinder pi into d dash. This is the diameter of the wire, not cylinder, and 4 times thickness into it is the initial stress in the wire. So this is the equation. Then you when your fluid is this is the initial stress. When the fluid is admitted, let the stress developed due to fluid pressure is in the wire is W, in the cylinder is called F1. So consider the force acting on half cylinder of the equilibrium. Then we write the equilibrium equation. This is the force Fw into wire, and this is the cylinder. Both are resisted by the fluid. P is the fluid pressure admitted into fluid pressure into the cylinder. D into L. So from that you calculate this equation C, Fw into pi d dash by 4 plus 2F1 into T into B. This is the put as the equation. That equation is developed. This is the half portion. When you admit the internal pressure of the cylinder, and Fw is also tensile nature, and F1 is also cylinder is also, both are in tensile nature. Initially, one is tensile and another is compression. But after admitting the fluid into the cylinder, hoop tensile stress F1 is the hoop tensile stress. So to form another equation in W and F1, the criteria is at common surface. This is the common surface. The strains are calculated. That once you know the W stress divided by Young's modulus of wire will give the strain at common surface. That is D, and circumferential strain in cylinder. So still cylinder already told here there F1 by E minus mu times, this is the Poisson's effect. Actually strain in a cylinder is F1 by E is enough. But it is acting F1 and F2, two forces. The lateral effect of the secondary effect of or lateral effect of the F2 will be mu times F2 by E. So where F2 is the longitudinal stress, P by ET. So again, you equating the equation D and E, then this is you get the equation F. So from equation C, you find the FC, and from equation the stresses in wire and cylinder fluid will form. So after finding this one, the final stresses are obtained by algebraically add initial stress and stress due to fluid. This is the wire wound problem. I will explain in uh, an example tomorrow. So దిస్ ఇస్ ద వైర్ వన్. కాపీ చేసుకుంటారా? స్టూడెంట్స్ కాపీ చేస్తున్నారా?
Yes, sir.
Right. This is the overall problem. ఇవన్నీ కాపీ చేస్తారా? డయామీటర్ ఎన్ని
Sure.
కాపీ చేయండి. This problem may ask or may not ask from the thin cylinders. I will not say it's a compulsory question, but compulsory question from this unit to thick cylinders. కాపీ చేస్తారంటే నేను I will go for next slide.
Yes, sir.
Draw the figure.
Yes, sir.
Right. Let's take the full circle. Let's consider half of the circle here and half equilibrium. Draw the figure. Initial stress. This is the initial stresses.
Yes, sir.
Right. Okay.
Yes, sir.
Strains. Your P is the internal fluid pressure.
Yes, sir. Yes, sir.
This is the theory about the thin cylinders. So in thin cylinders, two types of problems. One is formula substitution based form problems, and second is wire bond problem. I will explain in next class those. Now coming to the this is very important in exam point of view. Analysis of thick cylinders. This is very important. All of you put a heading thick cylinders. So for the thin cylinders shells subjected to internal pressure, the circumferential stress was calculated on the assumptions based on assumption uniform across the thickness of the metal. That is the previous slides, concept of the previous slides. And this is not strictly true. Actually, అలా ఉండదు, యూనిఫామ్ ఉండదు in thin cylinders also. So why? Because the stress is not uniform, but varies from maximum at inner side and minimum at outer side. This is the actual in the previous case in thin cylinders. The stress is circumferential stress is uniform throughout the cylinder అని చెప్పి అనుకుని మనం స్టార్ట్ చేస్తాం. బట్ ఇలా ఉండదు అక్కడ. థిన్ సిలిండర్స్లో యూ కెనాట్ యాక్సెప్ట్ లైక్ దట్. సో మరి ఎట్లా ఉంటుంది అది? మ్యాక్సిమం అట్ ఇన్నర్ ఫేస్లో మ్యాక్సిమం ఉంటుంది, అండ్ అవుటర్ ఫేస్లో మినిమం ఉంటుంది. సో the variation may be looked upon the negligible, but the stress is sensibly uniform. The thickness does not involve the PD by 2T in thin cylindrical shell. So now we shall consider thickness of wall is not small as compared to diameter of the cylinder. That is thick cylinders. So that means the thickness of the cylinder is not small when compared to the its diameter of cylinder. Such type of cylinders called as the thick cylinders. So the analysis of the fundamental thick cylinders is derived or to on the assumption section. That means Lehm's introduced section perpendicular to the centroidal axis of the cylinder, which is plane before pressure coming, remains plane after the shell under the pressure. So or otherwise you can think like that. The longitudinal strain at any point in the thickness of the metal is constant and independent of the position of the point. That is the Lehm's assumed. That's why Lehm's theorem. This is also called as a theorem. So you can assume all these things. Only assumption is the longitudinal strain at any point in the thickness of the metal is constant and independent of the position of the point. Adi kuda meeku one of the. So here in the analysis of thick, apart from the assumptions like material homogeneous at isotropic, all these things are you lesson and learn from 2-1 mechanics of solids, and proportionality which is not exceeds all important. In addition to that, the longitudinal strain is uniform across the cross section of the cylinder. So this is the main which is by Lehm's theorem. This is given by Lehm's. That's why it is called Lehm's theorem. This assumption is reasonably good for a large portion except near the ends, and the theory is based on this assumption is called Lehm's theory. So the thick cylinders can be analyzed on the basis of Lehm's theory. Simply you can remember the analysis of thick cylinders is done by the Lehm's theory. So what is Lehm's theory? Ante the longitudinal strains are uniform across the cylinders. That's enough. And consider the thick cylinder as shown in figure 1.2.0. Let write down all these things. R1 be the నేను చెప్తున్నప్పుడే మీరు రన్నింగ్ నోట్స్ రాయండి, టైం వేస్ట్ అవ్వదు. Let R1 be the inner radius, R0 R0 is the outer radius, and P1 be the internal radius, that is denoted by internal radius when R is equal to R1, and that means R1 అనేది మనం ఇంటర్నల్ రేడియస్ అన్నప్పుడు ఇంటర్నల్ రేడియల్ ప్రెషర్ కూడా P1 అనే ఇస్తాం. అట్లా ఇక్కడ ఆర్ నాట్ అవుటర్ రేడియస్ అన్నట్టు ఎక్స్టర్నల్ రేడియస్ pressure is called as P naught. So let us see here cross section of the cylinders. Yes, cross section cylinder. This is the internal circle and this is the outer circle. So internal fluid pressure is P naught. This is the P0 is subjected to internal pressure, and P naught is the outer ring subject to outer force, the external pressure, radial pressure, and R1 is the internal radius from center. It is R1, and R naught is the outer radius. Now consider a concentric circle elemental ring delta X with delta D, and the pressures will be acting in the cross section. You take the half of the cross section like this, internal fluid pressure Px, and increase the element. This is the elemental length. I want to derive the equation for elemental length dx. So this is the dx. I am consider x from the support, and the elemental length will be px plus the pressure on the elemental length is the px plus delta px. So from this all you can see derivation is not important, but you can copy all these things if you want to derivation. Finally, you get the equations are this one. Px is equal to, that means what is the Px? Radial pressure at any point is equal to B by x square minus A. This is the radial pressure. This formula will give the radial pressure. And F1 is the hoop stress or circumferential stress is B by x square plus A, where A and B are the constants. Where A and B are the constants, and X is the radius. So you can take want to find the pressure, radial pressure at inner radius. So put x is equal to r1. Then after knowing the constants, put x is equal to r1. Then what is the internal pressure at radius r1? అలాగే what is the hoop stress at x is equal to r1? Then what is the hoop stress at that particular point? So x is the variable and a and b is the constants. Anybody want to derivation? You take this figure and also copy the all these things. I will explain later. ఆల్రెడీ ఆ బొమ్మది నేను ఆ ఫిగర్తో ఎక్స్ప్లెయిన్ చేశాను, అదే ఇక్కడ ఉన్నది. ఆల్రెడీ ఐ ఎక్స్ప్లెయిన్ ఇన్ ఫిగర్. కన్సిడర్ ఏ సెమీ సర్క్యులర్ రింగ్ ఎలిమెంట్ with internal radius x and thickness is delta x. So let internal pressure on it be px, then external pressure on the circumferential elemental ring px plus delta x. Let L be the length of the element, then you calculate the bursting force or resisting force is equal to px into 2xl minus this is the internal and this is the external. So if F1 be the hoop stress in the element, then the resisting force already thin cylinder stays in there. F1 into 2x delta x into L. So equating both equation, neglect the higher order degrees, order terms, then you get the this one x plus delta p minus px. So equal to F1 into x. From this, you can write F1 plus x into delta px by x plus px equal to 0. Then you, this is the small delta. Then you apply the limits dpx by dx. Now you can differentiate. Now the consider longitudinal strain F2 is a longitudinal strain given by this one. Yeah, E2 is the longitudinal strain F2 by E into. This is the F1 force, strain due to F1 force, and this strain due to radial pressure. Then you can write E2 longitudinal strain in this line. So the Laims theory, the strain is assumed constant in anywhere. Therefore, so F2 is constant. Therefore, F1 minus Px should be also constant. Let this constant is taken as 2a. Let it be equal to 2a. దీనికి ఏమీ లేదు, వాడు 2a అని తీసుకున్నాడు. మరి సార్ ఇది ఎలా వచ్చిందంటే మనం ఏం చెప్పలేం. దట్ ఇది లాంగ్ స్ట్రెయిన్ ఈజ్ కాన్స్టెంట్ త్రూఅవుట్ ద సిలిండర్ కాబట్టి F2 is also obviously constant. F2 constant ఏంటంటే అవుతుంది, F minus Px is also constant. Thus constant is taken as 2a. So F1 minus Px is equal to a. From that F1 is equal to Px plus 2a. And substituting the equation a, this then you get this one, and simplify this one, and integrate it both sides, and integrating you get this one, F1 is going to be by x square. So this is the derivation of the Lenz's theorem. Finally, you remember these equation, what I am put in red marks. So to determine the radial pressure at any point, we'll give the b by x square minus a, and to determine the hoop stress in the cylinder, F1 is equal to b by x square plus a. That's enough. All of you copy that one. కాపీ చేసుకుంటారా లేకపోతే ప్రాబ్లంకి వెళ్ళిపోరా?
ప్రాబ్లమ్స్
కాపీ చేసుకుంటారా?
ప్రాబ్లమ్స్.
ఐ విల్ ప్రాబ్లంలోకి వెళ్ళిపోతాను. మీరు ఈ రెండు గుర్తుపెట్టుకోండి. మీరు ఇక్కడ ఎవరు డెరివేషన్ అడగరు, బట్ ఫైనల్లీ యూ రిమెంబర్ వాట్ ఈస్ Lenz's ఈక్వేషన్ అంటే యూ కెన్ రైట్ దిస్ వన్. Right, what Px is equal to b by x square minus c, and F1 is equal to b by x square plus c. That's enough. Clear? So where a and b is the arbitrary constant, x is the distance of the elemental under the consideration of center of the circle, that means radius. So the arbitrary constant may be determined by using pressure values. X is equal to r1. What is r1? Internal radius. And what is r0? Outer radius. Right. Keeping these points, this is the examination questions. ఇవి అడగచ్చు. ఎలాగ అడుగుతాడంటే ఇలాగ అడుగుతాడు. So let us see example. A pipe of 400 mm internal radius, internal diameter. మనం చాలా ఫాస్ట్గా వెళ్ళిపోతున్నాం. 10 అవర్లు వేసారు వేస్ట్. ఇది ఒక 3 అవర్లో తేల్చేస్తాను నేను. రేపుతో క్లోజ్ చేద్దాం ఈ యూనిట్. ఏమా? So a pipe of 400 mm internal diameter and 100 mm thickness contains a fluid at a pressure 80 Newton per mm square. Find the maximum and minimum hoop stresses across the section. Also sketch the radial and hoop stress across the section. This is the examination question. All of you copy this one. Take the Lenz's theory, that means thick cylinders, analysis of thick cylinders by Lenz's theory, and that problem. Copy చేస్తున్నారా? This is the problem. So internal diameter is given 400. That means internal radius is half of the diameter, you got 200, and thickness of cylinder is given 100 mm. So let us take outer thickness R1 plus T, 200 plus 100. So our inner radius is 200 mm and outer radius is 300 mm. And what is the pressure inside? Fluid pressure is given, P1 is given. So 1 is meant for the internal fluid pressure is 80 Newton per mm square, and P2 or P0 equal to 0. Okay, already there is no external pressure acting on the cylinder. And coming to the now use Lenz's equation, Px is equal to b by x square minus a to determine the constants a and b. After determining the constants a and b, you find the hoop stress. So first you determine the constants. For determining the constants, you use this arbitrary limits. So at x is equal to 200, that means x is equal to internal radius r1. So x is equal to r1 is 200. Then what is the pressure in the inside? 80 MPa, 80 Newton per mm square. So use this equation. You know the Px is equal to 80. You know the x is equal to 200. You don't know b minus a. You get equation 1. And x is equal to r naught. What is r naught? 300. Again, what is the pressure at outer side? 0. Therefore, Px is equal to 0. B by 300 square minus a equal to 0. Now equation 1, solve both equations. B by 200 square minus a and equal to 80. That is equation A. And b by 300 square minus a equal to 0. So solve these two equations, you get the constant AB. That's enough. You get the constant B and substitute any one of the equation, you get the A. Do it, all of you. What is the constant? Let us bring the calculator. All of you have calculators. Students.
సార్
అర్థమవుతుందా? కాలిక్యులేటర్ వేసుకున్నారా? ఇప్పుడు ఏం చేసాం మనం? లిమిట్స్ అప్లై చేసి కాన్స్టెంట్స్ ఫైండ్ అవుట్ చేస్తున్నాం. ఓన్లీ యూజ్ పిఎక్స్ ఓన్లీ, నాట్ F1. ఇంకా F1 పక్కన పెట్టండి. F1 పోర్షన్ ఎప్పుడు వస్తుందంటే ఆఫ్టర్ ఫైండింగ్ ద కాన్స్టెంట్స్ బి అండ్ ఏ, అప్పుడు వస్తుంది దాని యొక్క రోల్. ఇప్పుడు మనం బి అండ్ ఏని ఏబిలు కాన్స్టెంట్ మనం ఫైండ్ అవుట్ చేయాలి. దేర్ఫోర్ యూజ్ ఓన్లీ పిఎక్స్ ఈక్వల్. సో ఎట్ x ఈజ్ ఈక్వల్ టు 200, దట్ మీన్స్ x అనేది ఇంటర్నల్ రేడియస్. ఎంత ఉంది? ఇంటర్నల్ ఫ్లూయిడ్ ప్రెషర్ 80 ఉంది. అలాగే x ఈజ్ ఈక్వల్ టు 300, ఇంటర్నల్ ప్రెషర్ అంతా 0, అవుట్ సైడ్ ఏం ప్రెషర్ లేదు. కాబట్టి సాల్వ్ దీస్ టూ ఈక్వేషన్స్ అండ్ గెట్ ద b value. Once you get the b value, substitute, take any one equation and substitute the b value in the equation, you get the a value. What is the b and a? Please do it and tell me answer. Haripriya. Haripriya.
Yes, sir.
Calculate చేసావా b value? Are you understand? అర్థమైందా?
అర్థమైంది సార్.
Use this equation and find the constant b with the limits. X is equal to 200 and x is equal to 300. When x is equal to 200, put px is equal to 80, and x is equal to 300, put px is equal to 0. Solve the equation. ఎవరన్నా మనకి మన సెక్షన్ లో నేపాలీస్ ఉన్నారా?
ఎస్ సార్, ఉన్నారు సార్.
సి సెక్షన్ లో నేపాల్ ఉన్నారా?
ఉన్నారు సార్.
మరి వాళ్ళు ఇప్పుడు లైన్ లో ఉన్నారా? హలో నేపాలీస్, హౌ ఆర్ యూ?
Sir, sir, fine, sir.
Okay, are you listen the lesson? Are you understand?
Yes, sir.
Yeah. If you have a doubt, please ask me immediately.
Okay, sir.
What is the number?
H7, sir.
Huh?
H7.
H7, huh?
Yes, sir.
H1, H2, H2, H3, H3, 5. This is H7. How many members is there from Mapoli?
4 members, sir.
So what are that numbers? Because I don't have registered. That's why I'm asking.
Only I am present, sir, today.
Okay, you only present, eh? Okay.
Sir.
Right. And solve the equation and get the A value, B value, and A value. చెప్పండి ఎవరని ఎంతసేపు అండి అది
A64 సార్.
A64
ఎంత
వచ్చింది సార్.
వచ్చింది?
బి చాలా పెద్ద వాల్యూ వస్తుంది సార్.
ఎంత చెప్పండి పోనీ పెద్ద వాల్యూ అయినా చెప్పండి ఎంత
576.
బి వాల్యూ 5760000
సార్.
సార్.
Okay, but A is getting 64, right?
సార్.
So like that you like that you find the
వచ్చింది సార్.
64 వచ్చిందా A?
వచ్చింది సార్.
Right. Now you know the constant B is equal to something, A is equal to 64 something, what it may be. So now put in to determine the variation in the radial pressure, Px is equal to B is substitute B value in that B value in the case of B, and put in terms of A value 64. Then you again you determine the variation pressure. This yeah. So this one, this is the one equation, B by 200 square minus A, and x is equal to 300, Px is equal to 0, B by 300 square minus A, and subtracting equation 2 from 1, you get this value 5760000 is a B value, and A value after getting the substitute in equation 2, that you get the 64. So now after getting the A and B constants, the variation in radial pressure is given by Px by, again this is the equation 5760000 by x square minus 64. This will give the variations of radial pressure. Now at x is equal to 200, that means x is internal pressure, Px is equal to, already all of you know this is 80 MPa, and at x is equal to 250, I want to find the radial pressure at 250 mm. Then use this equation and find. So this one 250, put simply x in the place of x, we put 250 minus 64, that is 28.16. See, at 280, at 250, 28.1 MPa, Newton per mm square, and x is equal to 300. It is the outer radius, there is no external pressure, therefore it is 0. So this is the variation of the radial pressure. And coming to the variation in the hoop stress, now you know the Lehm's equation to determine the hoop stress. Fx equal to B by x square plus A. What is B? This one. And what is A? This one. Only variation is difference is instead of minus, you get positive value. That's enough. So again you determine the variation of the hoop stress at same points. At x is equal to 200, internal pressure, you put simply 200. It is so already I told in the thin cylinders analysis, in the analysis of thin cylinders, we assume hoop stress is uniform throughout the section, but not like that in actual situation. Maximum at inner surface and minimum at outer surface. Let us conclude that one. So at x is equal to 200, that means inner face, the hoop stress is 208 MPa, and at 250 mm radius, at radius 250 mm, then it is 150. It dropped from the previous one. And x is equal to 300, that outer side is one. So maximum hoop stress at inner side and minimum hoop stress is outer side. This is the variation of the hoop stress. So the variation of hoop stress is shown in this figure. So it is inner, and this is the outer. So inner radius is 200, 80 MPa is radial pressure, and at x is equal to 250 at 28.16, and 0 at outermost radius. So this is the variation of the radial pressure distribution. And hoop stress variation, same at inner face 208, and at 250 156, and at 300 128. So it's not zero, it's a trapezoidal shape hoop stress distribution, and this is the triangle shape is given for the radial pressure distribution. So this is the question asked from thin cylinders. కాపీ చేసుకుంటారా అని రైట్. వెరీ సింపుల్ గా ఇది 15 మార్కులు అనవసరంగా. వై యూఆర్ నెసరీ లూజ్ 10 మార్క్స్ for 12 marks or 14 marks, whatever it may be. Very simple.
స్క్రీన్ షేర్ రావట్లేదు సార్.
No, no screen share.
No, sir.
No, 1 minute.
Question, sir. Questions.
Here I will put in. Right. I will put in red mark because we are using this equation 28 font. Right. Here also x is equal to exponential. This is the equation used. Right. Five, 7, 6, 0000 divided by x square minus x64. Using this, వస్తుందా? చేంజ్ చేయమంటారా స్లైడ్, లేదా ఇంకా కావాలా? అవుతుందమ్మా, నెట్ వస్తుంది. జియో వేరే జియో అవుతుందా? నువ్వు అది క్లాస్ ఉంది ఇప్పుడు? క్లాస్ అని ఉందా అనంతగా? ఇందులో లాగిన్ అమ్మా. By using lens constant, but design, how it is designed, design of thick cylinder. What is the design of thick cylinder? To design the thickness or radius of thickness of the cylinder. Thickness enta pressure peduthe, enta pressure unna cylinder ki enta thickness unnadane design. So that is analysis. This is the design. So let us take an example to the thick cylinder of hello evaradi ఓహో మా దగ్గర నుండి. సారీ మా రోడ్డు మీద ఎవరో వెళ్తున్నారు. అది
మీ దగ్గర నుంచి కాదు సార్.
కాదా? ఏదో రోడ్డు మీద బయట వెళ్తున్నారు. రైట్. Right. So a thick cylinder of internal radius is 160 mm, is subjected to an internal fluid pressure is 40 MPa Newton per mm square, and allowable stress in material is 120 MPa. And that cylinder and material allowable stress working under safe material, stress in safe material is given 120 MPa. Find the thickness of the cylinder. This is the design problem. So how it is? ట్రైన్స్ తిరుగుతున్నాయా? ట్రైన్స్ తిరుగుతున్నాయా? అబ్బో, అది నేనే బయటకు అడగలేదు భయపడి. నాకేం తెలియట్లేదు, బస్సులు తిరుగుతున్నట్టుగా ఏమి ట్రైన్స్ తిరుగుతున్నట్టుగా ఏం తెలియట్లేదు నాకు. అయితే అన్ని తిరిగేస్తున్నాయి. కోవిడ్ పోయింది.
సేమ్ భయం పోయింది సార్.
కరోనా అంటే భయం పోయింది. ఏం లేదు, అంతా కూడా అంటే లేదు. ఇది మ్యాన్ మేడ్ వైరస్. ఎంత సవాళ్ళ మీద అంటే ఒక కార్పొరేట్స్ ఎలా ఉంటారన్నది ఎఫెక్ట్. ఎంత జాలి దయ లేకుండా వాళ్ళకి కావాల్సింది ఓన్లీ పైసలే, డబ్బులే, మానవ జీవితాలు కాదు. చూడండి ఈవేళ ఎలా నెట్టారో మనకి. ఇది మ్యాడ్ మేడ్, నాట్
సార్.
Okay, right. So okay, I will complete this problem and stop. A thick cylinder of internal diameter 160 mm is subjected to internal pressure of 40 MPa and allowable stress material and that is called safe stress in material is given 120 MPa. D1 is the internal diameter is given 160, 80 is the radius, and given the internal pressure 40 is given, and minimum the is given, P maximum is also that means safe allowable stress in material is but nothing but safe stress is taken as maximum stress built by that material or resisted by material is given 120. So from the Lehm's equation, you know the radial pressure calculated by this equation, and the hoop stress is calculated this way. The hoop stress is coming to the play when you know the arbitrary constants A and B. So now it is not considered. Just the work is from this equation. Px is equal to b by x square minus a. So apply the limits at x is equal to internal radius, that means inner radius r1 is 80, the fluid pressure is px is equal to 40. Therefore substitute in this equation 40 is equal to b by 80 whole square minus a, that is equation 1. And here the hoop stress at inner edge is maximum because the hoop stress safe bearing capacity, that means safe stress in material is nothing but it's a hoop stress. That is observe here. The safe stress in material means that is the hoop stress, where it is maximum inner stress that maximum. All of you know already in the previous problem, you know where you get the maximum hoop stress at inner radius. So this is maximum hoop stress given by the problem. That is equal to the this one. So here the in the previous problem the safe allowable stress is not given. Therefore, you use this equation only and find the constant. But in this problem, safe stress in material is given, allowable stress in material is given. Therefore, use these two equations for to solve the arbitrary constants A and B. So, from equation 1 and 2, you get the constant A and B. So, from equation 1 and 2, B is 512,000, and I am using equation 1, A is 40. So after finding the constant B, then what is the radial pressure at outer surface, and what is, if you want to find the radius thickness, he's designed the thickness of the cylinder. Therefore, uh, uh, you know the R radius of the outer thickness. So radius of the outer radius of the cylinder. So to determine the outer radius of cylinder, let us use uh, the external the pressure at external surface is 0. Therefore, you know the B, you know the A, and use radial pressure equation and find the R naught and R. So the thickness of the cylinder R is given by P is given by R naught outer radius minus inner radius, which will give the 31 point. Like this, you design the thickness. Okay. Very simple problem to determine the thickness. Can you change the slide?
Yes, sir.
Yes, sir.
world itself divided into two groups. One is who is taken vaccine for corona, one group, and who are not taken vaccine for corona, other group. So if any a thick pipe of 300 outer diameter, a thick pipe of 300 outer diameter and 200 internal diameter. So a thick pipe of 300 outer diameter, 200 internal diameter is subjected to an internal pressure. Is subjected to an internal pressure of 12 MPa. Okay.
Yes, sir.
Okay, now?
Okay,
A
sir.
thick pipe of 300 in outer diameter and 200 internal diameter is subjected to an internal pressure of 12 MPa. Full stop. What minimum external pressure? What minimum external pressure? What minimum external pressure can be applied? What minimum external pressure can be applied so that the tensile stress in the material in the material shall not exceed shall not exceed 16 MPa. Clear? Students,
Yes, sir.
can you do the problem? ఇప్పుడు నేను చెప్పిందే నేను ఇక్కడ థిక్నెస్ అడిగాను, అది థిక్నెస్ కాకుండా అక్కడ ఎక్స్ట్రా ఎంత ఎక్స్టర్నల్ ప్రెషర్ మినిమం ఎక్స్టర్నల్ ప్రెషర్ ఉంటే ఇది 16 MPa మెటీరియల్ 16 MPa రెసిస్ట్ చేస్తుంది అని చెప్పాను. ఇదే ప్రాబ్లం డిఫరెంట్ వేరే అడిగాను. చాలండి మరి. టుమారో విల్ డిస్కస్ ద ఓవర్ ఓన్ ప్రాబ్లం and compound problem in